So what we're going to do for this is, like, right now, if I ask you to tell me what the square root of 1.1 is, you can just type that into your calculator really fast. You would get a correct approximation out to many decimal places, which would be, more than we ever probably even really need to know for anything that we do. But calculators have not always been available, so that is where this section comes from. It's actually called differentials in your textbook, and it goes into a lot of like error stuff, which is a little more applicable, but we don't have to do it for this class, so we're not going to go into some of the detail that the book goes into, but we are going to do the linear approximation part. So we're going to find the linear approximation to f of x equals the square root of x at x equals 1 and use it to approximate 1.1. So this is what we're going to do. Oh, yeah, you don't need that, aren't you? I am recording. I just don't have this projector on. Let's see. Let's do this. I'm going to just type in y equals the square root of x. And right here, I'm just going to put, I'm going to put y equals 1.1, just so, no, I want x equals 1.1, just so we can kind of see like where we're at here. As I zoom in here, like, I can see clearly right here the line is curved, or right here really I can tell the line is curved, right? But if I zoom in, like this, does it look curved? It looks very linear, right? So the idea is that it's really close to a line here. So even if I'm zoomed out, like right here, where right here is 1. If I get this picture, I can tell maybe it's not quite a straight line, but it looks awfully close to being a straight line, right? So what we can do for this is, let's say that we are stuck back in the early 1900s and we don't have a calculator, then what I can do is I can take that equation, y equals x squared, which looks like this. No, it doesn't. Got that point right there wrong. There we go. So y equals x squared looks like this. And I can find the tangent line at 1. Which we know how to do tangent lines already. I can find this tangent line at 1. And a line is really easy to plug a number into, right? It's just y equals mx plus b. So if I'm really close to 1, it's going to give me a number that's really close to being the right answer. So it'll probably be good enough for what we're actually going to use it for, depending on our situation. So what we're going to do is we're going to find a line tangent to this graph at x equals 1. So to find a tangent line, what have we got to have? Derivative. So we're going to take the derivative f prime of x would equal 1/2 x to the negative 1/2 there. Or I may want to write this as 1/2 times the square root of x. So that's my derivative. I'm writing the tangent line at 1. So I'm going to plug 1 into this. F prime of 1 would be 1/2 times the square root of 1, which would give me 1/2. What does that tell me about my tangent line? What is 1/2? That is our slope. Okay? Right, because derivative gives us the slope of the line. What other thing do I need to write the equation of a tangent line? The point on the line, right? So that's just f of 1, which is the square root of 1, which equals 1. So my point on the line is 1, 1. All right. Right I'm ignoring this approximate 1.1. I'm not using it at all. I'm just finding the tangent line at 1. So now I'm going to write the equation of my tangent line. So that would be y minus 1 equals 1/2 times x minus 1. And this is my tangent line right here. So, while I do not know how to find the square root of 1.1, I could plug 1.1 into this equation pretty easily, right? So, if I do that, I'll have y minus 1 equals 1/2 times 1.1 minus 1. So, y minus 1 equals 1/2 times 0.1. So, y minus 1 equals half of 0.1 would be 0.05. And I would add my 1 to both sides. So y would equal 1.05. And actually I should, instead of using equal, should use like the little squiggle. Because this is an approximation. It doesn't actually equal 1.05. So the square root of 1.1 is about 1.05. Now, it would not be a good idea to use the same line to approximate 9.5. Because once you get out here to 9.5, the line's way off, right? But anything pretty close here, it's going to give a pretty good approximation. If we get our calculator and just type in the square root of 1.1. See, we're pretty close. For most things we would need to do, we'd round that to 1.05 and it would be good enough. Now, if we need to be really precise, we would have to go further in depth. And you actually can sort of do this process over and over to get a more accurate estimation here. But we're not going to go into that because we don't even really need to do this because we have calculators, right? But the idea is still an idea that's important to calculus, even though we can approximate these on our calculator really quickly. And these problems are usually pretty easy because you guys have done really well with tangent lines. If you see a tangent line problem at this point, most of you probably think it's a pretty easy problem. So it's just a tangent line problem, and at the end you plug in whatever value you're looking for. We will see these presented in a couple of different ways. You might see something like this where it just asks you to approximate the square root of 8. And it says using linear approximation. So if I'm asked to approximate the square root of 8, I would not want to go back and use this line here because out here at 8, my line is off, right? So whenever I have a problem like this, when I have a problem like this, I want to think, what is the closest whole number that would work here? So if I'm approximating square root of 8, what's the closest thing I could use? I'd use 3, which is square root of 9, right? I'd use a 9. So my equation here would be f of x equals the square root of x, and I would be using the value x equals 9. All right, so I would use that for a tangent line. So for the tangent line, it's the same derivative that we just found. So it's 1 over 2 square root of x. We would find f prime of 9 this time, which would give me 1 over 2 times the square root of 9, which is 1 over 2 times 3, which is 1 over 6. And then I also need f of 9 to get my point because this is my slope here that I just found. So f of 9 would just be the square root of 9, which would be 3. So 9, 3 would be my point. And that means my tangent line equation would be y minus 3 equals 1/6 times x minus 9. All right, questions here? Okay, so then we just take 8 and plug it in. So y minus 3 equals 1/6 times 8 minus 9. So y minus 3 equals 1/6 times negative 1. So y minus 3 equals negative 1/6. We'll add the 3. So y will equal 2 and 5/6, which I don't really like to use mixed numbers like that. So that would be 12/17/6. Or you could get decimal if you wanted. So let's see how close that is. So if I've got 17/6, that gives me 2.83 repeating. The square root of 8 is 2.82843. Still pretty good, right? It's pretty close. Although this is not necessarily so useful for us in the days of calculators, I do find it pretty fascinating. I find all of math kind of fascinating. Like, people came up with this. It's not that hard. It's not easy, but it's not that difficult for you guys to follow and see where that came from. But somebody, first of all, had to have the idea they needed to know the square root of 8 for some reason, when nobody else had known it before. And then they had to come up with a way to figure out what it would be close to. And then what they took from that is they found ways to get closer and closer and closer until they could actually give what they considered like you can't actually get it's an irrational number. It keeps on going forever. So you could never get the exact decimal approximation, but you could use this process as many times as you needed to get it as accurate as you needed it for whatever you was.
Know the exact square root of 8.
Not a decimal approximation, because it is irrational. Anything that is an irrational number keeps on going forever. So it would go on and on and on. Pi is the same. Although I don't know if technically pi has been proven to never end, but everyone, because they've never found the end, and they've got computers like calculating digits of pi forever. So likely it doesn't end.
I think one day it'll just stop.
One day we might find the end of pi, and then the world will explode. Yeah. Yeah. So. All right. So, in example 3, here I just want us to think about if we have a tangent line that looks like its tangent maybe about right here. This looks like the first problem that we did, right? Is that tangent line an overestimate or an underestimate?
Over.
It's over, because the line is above, right? Example 4 is, let's split it right here. If I'm over to the right side, it's an overestimate. If I'm over to the left side, what would it be? An underestimate. So, if the graph is concave down, the estimate will be an overestimate. Because when you have something that's concave down, the tangent line has to be above that graph. If the graph is concave up, the estimate has to be an underestimate, because if the graph is concave up, then that tangent line has to lie below. So not only can you know a pretty close approximation, if you take a second derivative and plug in that value, you can know how close you are to, or whether it's overestimate, whether you're too high or too low. There. So let's do this. It's really not that difficult to plug 2.1 into this equation, but I wanted something that we could do fairly easily. Imagine that we have a super complicated equation. It would be a lot easier to plug 2.1 into a line than something where we've got to take the square root and raise something to the fifth power or something like that. So what we're going to do here is we're going to find our equation of our tangent line. Actually, we don't have time for this one, do we? Yeah, we don't have time. I think we can do it really fast. F prime, this is the easy one. It's going to be 6x plus 4. So F prime of 2. We're going to use 2 because that's the closest whole number to 2.1. It would be 6 times 2 plus 4. So we get 16. F of 2 would be 3 times 2 squared plus 4 times 2 minus 2. So we get 12 plus 8 minus 2, so 20 minus 2 would give us 18. So 16 is our slope. 218 is our point. And so what we'll do here is we'll have y minus 18 equals 16 times x minus 2. And then we'll plug in 2.1. So y minus 18 equals 16 times 2.1 minus 2. So we get 16 times 0.1. So y minus 18 is 1.6. We add 18. And y is 19.6. If we take 2.1 and actually plug it in, I did something wrong. I don't know what we get, but that's okay. Will be this is right. Yes, this is what I want you to do here. We missed that last example, which is a trig example, but it's going to be the same thing. Find the tangent line, plug that number in. So I think you guys will still be able to do the assignment.